Hello, everyone, and welcome to today's Tech Talk on commissioning cross-flow heat exchanger cores. My name is Sherry Adams, and I'll be the moderator for today's session. Please note that throughout the Tech Talk, all phone lines will be muted. This will minimize any background noise or feedback that could distract from the presentation. When you first joined the Tech Talk, an attendee control panel appeared on the right side of your desktop. On the other side of this control panel is a small tab with an arrow icon at the top. Pressing this icon allows you to minimize and maximize the control panel. When maximized, you can use the control panel to submit questions. We will be gathering your questions throughout the Tech Talk, and we'll leave a little time at the end for Q&A. If your question is related to a particular slide, please include that number of the slide in your presentation. Also, a PDF of the slides from this presentation will be sent electronically to all those who are registered for today's Tech Talk. We will also be recording this, and it will be available on our website under the resource section. There is a new password to access the Tech Talks, and it will be emailed out to all members after this presentation. Today's presenter is Kevin Thurston. Kevin is the owner of Thurston Engineering Services, located in Saskatoon, Saskatchewan, Canada. Kevin is professional engineer, certified energy manager, and certified commissioning professional. He's been commissioning throughout Canada for more than 18 years. Kevin is the past president of the Western Canada chapter and is currently the president of the board of directors for the Building Commissioning Certification Board. Thurston Engineering Services is a certified commissioning firm. Kevin's most recent projects include ongoing commissioning of the new Ramey Modern Art Gallery of Saskatchewan, the University of Saskatchewan's new ice hockey facility, and over 1 million square feet of schools in 2017. So Kevin, I'm going to turn this over to you now.
Thank you, Sherry, and welcome everybody from across North America or in the world, wherever you're listening and whatever time zone you're in. Today's Tech Talk is going to be about commissioning of cross-flow heat exchangers. And what I'll do today is I will have a brief introduction and the basics of a cross-flow heat exchanger for those that may not be familiar with them. The design conditions to which they were designed to for temperature and whatnot and airflow. The impact of the return air dampers as well as the return fans on energy recovery, monitoring the pressure differential across the cores, on-site measurements that were made, optimizing the flows across them, and what the energy impact of an imbalanced flow was across the heat exchanger. So the following 6 slides are going to depict the basic operation of an energy recovery system using energy recovery cores. And these were based on 41 systems that were installed in schools across Saskatchewan. After the initial year of operation, the energy consumption was about 20% higher than what was anticipated. In some schools, it was more. And because of this, an investigation was required about 18 months after substantial as to why all of this was happening. So for the basics of the energy recovery core, when the system is either shut off or shut down or in standby, for example, when you're outside of your normal operating hours like a school is, the dampers, which you can see in the middle of the drawing, are in a vertical position. And what this does is it keeps the cold outdoor conditions from penetrating into the air handling unit and being distributed into the school on startup. For the cycling for energy recovery, in this diagram, it assumes that the system has already been operating, and you have the cold outdoor air coming into energy core A, which is the top right-hand corner of the diagram, and then taking the energy out of the core, it's transferred into the airstream, which then mixes with some return air and is supplied to the school or to your building. On the other side of it, energy core B, it's in its charging cycle. So the exhaust air or return air from the building is directed through the core and then exhausts out. And this charges it, getting ready for when the cycle flips over. So when the cycle does flip over, you can see now that the exhaust air is traveling across and right through energy core A and being exhausted out. The heat is then being captured in energy core A. The previous slide where energy core B was charging, we now have our cold outdoor air coming across that, picking up that heat energy to preheat the cold, and then it mixes with some return air and is supplied to the building. So this cycle switches over every 60 seconds, and what that does is it helps prevent frost buildup and something that you don't then have to worry about for this type of energy recovery system, whereas say with a heat wheel or other systems, you may have to have some frost prevention. There is also a free cooling phase when the temperature and humidity conditions are sufficient that you can bring in 100% outdoor air without any pre-treatment. The cycle changes from 60 seconds then to 3 hours, and then it would flip again just to stop any like dirt or debris that might build up on the outside of the energy cores. The placement here of your sensors, your temperature sensors, and we will talk about this a little bit later on, is really, really important because it can help not mislead you to making some incorrect assumptions. So this is the free cooling mode. And then you have a full recirculation mode. This is ideal for like a morning warm-up so that your heating coils don't get blasted with cold outdoor air right away. You would have these dampers in this position where all of the return air is directed into the school, and it preheats prior to any teachers and students or building occupants arriving. So the design data, the important thing here is in the top part of this shop drawing is that we require to have a certain amount of supply air supply air coming off of the core, which is our outdoor air ventilation, as well as a specified amount of exhaust air. And if you look at the bottom of that snapshot of the shop drawing, you'll see that the pressure drop associated with the supply air coming through should be 0.74 inches water column, and on the exhaust side, 0.51. So the supply air actually does have more volume coming through it and less of the exhaust air going through that. But important here is that the minimum amount on the design of going through the core is 6,200 CFM. If you don't have that, you will not get your heat recovery that you're desiring. So for temperatures, it is designed to as cold as -35 Fahrenheit, and at that we should be getting roughly a discharge temperature, which I'll show on the next screen. But we're looking at 47.5 Fahrenheit coming off that core, and I'll show that on the next slide. You may wonder, does it actually get that cold for very long? I downloaded energy or hourly weather data just for 2019 for Saskatoon, where I'm located, and with a design of -35, we've already had 17 hours in 2019 when our outdoor air temperature was equal to or below -35 Fahrenheit, which is -37 Celsius. And if I just lowered that a little bit to -30 Celsius, we've already had 180 hours, and most of that was in February. It actually broke a cold snap 100-year record, so lucky us. So basically what our design conditions for our winter is we're bringing in 72 Fahrenheit or 22 Celsius return air. We are capturing heat recovery off the core and supplying that at about 47.6 Fahrenheit or 8.7 Celsius. And I'll show you some snapshots from the building automation system when we were doing this that actually shows what we were getting off of that core. So what do the cores look like? There are 2 cores per air handling unit, and this is what they look like. They're basically an aluminum core, like corrugated fins that are inside this housing. And you can see on the left-hand side of the picture, you can see the outdoor that would come across the core and then discharge on the right-hand side. Reverse, if exhaust air is coming out across that, it would be coming from right to left and exhausting out. So there are damper linkages that are factory installed that the controls contractor has absolutely no control over. They give basically the air handling unit an enable signal. And when they give it that signal, the 60-second cycles begin. The recirculation mode, unfortunately, is not programmed yet into this. It was not part of the approved sequences, but it is a recommendation to help out. So the little black dials that you see in the bottom left and right-hand corner, those can help adjust that 60-second cycle to optimizing the system, but it's factory set at 60 seconds, and that's what was stuck with, I guess, with the installation. Across the bottom core, where I showed you the picture of that energy recovery core, is a pressure differential meter. And unfortunately, this was not representative of what the actual pressure drop was across the core because it's not measured relative to the outdoor air. The air handling units are located on the roof of the schools and are connected to a stairwell. That's how you enter into it. And there's a very big plenum or access section attached to it for accessing the variable frequency drives and the motors and all of the access panels. So when this is measuring 0.1, this is actually in the exhaust state. When it's in the supply state, it reads a negative number just because of the way the pneumatic tubes are connected. When it goes into its supply, we would actually get an underflow warning and couldn't figure out why that was happening. So we want to be measuring the pressure across the core from left to right. You can see where the daylight is. That's where we want it measured because that's relative to outdoor air. So what we did is drilled holes on either side, and hopefully in the middle there you can actually see those two little holes that were drilled. And we installed our tubing across that with a measuring device that we got from a flow hood that we use for verifying balancing. So balancing the core. The next set of screenshots are going to be actually from the building automation system, as well as pictures of our measurements and a calculation showing how much flow we were getting before and after. This is also going to show the importance of the return air damper, its position, and the effects of it on the amount of heat recovery we get. We'll also show the importance of the return fan VFD speed and the effects of adjusting it. Prior to the final set of sequences, the return air damper was supposed to modulate to ensure enough air was across the core. However, in the final set, it got changed to being controlled on the building pressure, which kind of threw out the balance and one of the whole reasons for this tech talk. So our baseline condition, this is the snapshot from the building automation system. You can see right now that in the very center, our return air damper is at 100%. And the return air opening is actually sized for 100% of the air handling unit's flow because when you're in full recirculation mode or free cooling, you need to be able to close that off or open that up or bypass for some reason as in recirculation to bypass to do 100% of the air. When you are not in one of those modes, you need to have that damper at a position that is not 100% to get your pressure drops. And that's what we'll start changing when we're doing our trials. So you can see right now, just to the left of that red heating coil, you can see it says MA temp. That's supposed to be mixed air temperature. But knowing where that sensor was placed was incredibly important because it's actually placed right where it comes off of the energy recovery core. So it is not a mixed air temperature. It's actually the discharge temperature from the energy recovery core. And the way we discovered that was one of us was inside the housing right beside the core discharging when it was minus 10 Celsius out. And for the first 15 seconds, the air coming off of that was nice and warm, but then it dissipated, and by the end of the 60-second cycle was actually at about minus 10 Celsius. So we knew that the cores were not fully charging. So we took pressure readings for the baseline, and you can see that for supply, we had about 0.476 inches water column, and the design was supposed to be 0.76. So instead of the 15,000 or so CFM we should have had, we were only getting just under 9,600. For the exhaust side, similarly, it was low, 0.21 over the design of 0.51, and we were at about 4,900 instead of 11,800. Now, if you recall, I said the minimum amount of flow through the core was 6,200 CFM. Without getting that, we were basically not getting any heat transfer, and that was the reason why our mixed air temperature was so low off the core. So our first position to override the damper, you can see how the damper output is now changed to 80% and it's orange and indicates that it's an override. You want to see what that effect is going to be. And you may wonder how we came up with 80%. Prior to us going in and getting pictures and snapshots for this tech talk, we'd already spent a lot of time on other schools finding out what that damper position should be. So that was our starting point, and then we worked down from there. So you can see that the mixed air temperature off the core has now jumped up to 9.5 degrees from 6.5 degrees Celsius or 43.7 degrees Fahrenheit. So we're seeing some positive impact. However, our return fan speed is starting to decrease because we're still controlling the building pressure, and we're not going to get exactly what we need yet. So our measurements across the core, we now have increased our supply airflow up to 12,540, which is a significant increase, and our exhaust is almost at what the minimum is across that. So we had an increase in our supply air temperature off the core, but we're not quite there. So we lowered it to 55%. The mixed air temperature increased. The return fans continued to decrease down to just under 60%. And our results now we were getting much closer to the design, 11,850 across the core with that measured pressure drop. And we were up to 8,010 CFM, which are now above the minimum amount. The 45%, we can see now our mixed air temperature actually jumps quite significantly. We're just under 12 degrees Celsius, and our return fans came up slightly. So what was the impact of this one? We have now gone to just under 13,000 on the core and just under 8,000 on the exhaust flow. So basically all we've done at this point is we've adjusted the return air damper. Now we wanted to play a little bit with the return fan, start bringing it back up to where it was and see what that will affect. So you can see we played around with 75% and then 70%, and the mixed air temperature basically went from around 7.5 to 9.5 Celsius. And now our measurements we got is we're at about 11,000 CFM through the core for supply. That's 100% that's the outdoor air. And then on our exhaust, we're at 11,289. And what that is, our design is 11,800. So we're really, really close to getting our design conditions on the exhaust. And what that kind of showed is that it takes an awful long time to play with these numbers to get where you need to be. So having your balancers provide the minimums and knowing how the return fan should react is incredibly important to get that heat recovery. So what were the impact on the boilers for the hot water heating system? We chose an analysis period in February when the outdoor conditions were predicted to be roughly the same from Environment Canada. All 5 of the air handling units in the school were adjusted to what we knew were roughly the return air damper settings for a 2-hour period from about 1 to 3 p.m. in the afternoon. And the boiler plant was monitored to see if one boiler could handle the entire load of the school. The hot water supply set point, because the cores were then roughly balanced, we were able to lower it from 140 Fahrenheit or 60 Celsius down to 113 Fahrenheit, 45 Celsius. And that trend data was then exported to Excel for analysis. So on the next 4 slides, I'm actually going to show you what the trends looked like and what we were looking at. So on the left-hand side of the screen is February 7th, and then on the right hand is February 8th. And on February 8th, between about noon and 3 p.m. or 1 and 3 p.m., you can actually see the brown line, which is the hot water supply temperature set point, where we manually adjusted that to see if it could handle it. The orangish colored line is the primary lead boiler, boiler 2, and boiler 3 is the secondary one. So you can see on prior to our adjustment, 2 boilers were firing and sometimes 3. You can see the red line, which is the 3rd boiler that could come on, which cycles just massively as a result of a programming in the sequencing that compares a temperature differential from a primary and hot and secondary temperature system. So this is another issue that we found that's causing a lot of energy consumption. Okay, so you can see here that what we're seeing for the boilers is we actually get a % of the fire of each one of them. And so what we did was we wanted to look at if we could just shut one off, which you can see the boiler 3 goes to off in our trial period. Each one of these boilers is 2 million BTU per hour. So it's quite a significant boiler plant. There are 4 boilers in Saskatchewan because of how cold we get. We have what they call an N+1 design requirement, where if you design your building and you need 3 boilers, you've got to have a 4th one in there just in case one fails. So this is an N+1, and we have 4 2 million BTU per hour boilers, or 8 million capacity if all 4 were firing. So this is the actual trial period. You can note there's 2 times when the secondary boiler tries to restart, and this was a result of that programming where it's looking at a temperature differential and trying to bring it back on. So while this was going on, we actually had to override it to get it back off because we wanted to see if one could handle the entire load. The actual outdoor temperature at that time was around minus 25 Celsius, which was pretty cold. So what we got from that was with the hot water return temperature plotted on this one. You can see the dark blue line is the supply temperature and the red line is the return temperature. Interesting note that if you look on the left-hand side of this trend, if your return water temperature is on the left-hand side, that scale is degrees Celsius. If you are not below 49 degrees Celsius, you will not be condensing. So our boiler plant would have a maximum efficiency of 85%. However, with all of that cycling and the staging that was happening, we don't believe that it's anywhere near 85%. So if you can get below that, which you do see it dipping below that 50-degree line at times, then we can get our boiler plant efficiency up to a condensing efficiency of 93%. And in the trial period, you can actually see where when we made the adjustments to the supply water temperature set point, we dropped down well below that and had condensing throughout that trial period. So what did we get with our results? When we exported the trend data to the Excel file, we were able to look at the firing rate of the boilers from between 1 to 3 p.m. on February 7th. That was the baseline, and then the same time frame on the 8th. The firing rate, the trends basically showed only when there was a change of value in the firing rates. So we were able to take that firing rate times the boiler capacity. If there was 1 boiler, then it's that, and if it's 2 boilers, then it's the product of the 2 of them, times the time interval that they were at that stage. And what we found was that on February 7th, the consumption for those 2 hours was 4.3 million BTU, and on February 8th, it was 2.5 million BTU. So the savings from that was just over 40%. And as I said at the beginning, we were a good 20% worse on our gas consumption than predicted. So this definitely was a positive step towards correcting that. One thing we did notice that this was possible only because we had the cores all balanced. That would allow us to do this, or the school would get too cold. There were no complaints during this period of any zones being too cold. So the conclusions of this is that you need to ensure that the return air damper is balanced to have the design flows across the energy recovery cores, or you're just not going to get it. The tab contractor needs to provide that maximum value that the damper should be open when the cores are active, so i.e. somewhere around 80% or lower. The return fans would also need to have better control, not to the building static. And how one small change made by the design engineer can affect the energy consumption of the system when that return fan went from being an offset from the supply fan to being controlled to building pressure. So another thing that we noticed is, and I'm just going to go back to this slide right here. If you can make out from about 5 p.m. or 6 p.m. on until say 6 a.m. or 6:30 in the morning, you can see that the return temperature is well above that 50 Celsius for most of the time. When these air handling units are off outside of their schedule, the building is heated by radiant in slab heating, and that set point is more in around a 45 degrees Celsius set point. So if you could have it controlled that your hot water supply temperature set point from your boiler gets decreased, then you're going to have even more significant savings almost every night as this is happening. Any questions?
Thank you, Kevin. We do have a question. With condensing boilers, why would you want to force only 1 boiler to fire at a time, or was that just for testing?
Okay, so that was for testing, but we were having boilers that were cycling sometimes in 1 hour they were cycling 20 times on and off, and that's the pre-purge and post-purge. So we needed to see if by doing something like this we could smooth it out so that we wouldn't have that vicious cycling. Typically with a four boiler plant, you would have the manufacturer would typically control the staging to maximize efficiency. In this case, that was given to the controls contractor, and we've battled that ability to control the staging. They tried to give it like if the lead boiler got to 95%, bring on the secondary boiler, and then they would both kind of go at 50%. And it was when you would shut it off, which was, I think, one of the major issues with trying to control them. They also then implemented a temperature differential that I talked about, that we felt was more predictive than actually reactive to what was happening in the building. And you just couldn't get enough valves open in the radiant in floor to handle the increased flow and take off that temperature. So another boiler would come on and then shut off, and we would get this vicious cycling, which is probably 10% onto the consumption of the plant.
Okay, another question came in saying, why a 60-second cycle rather than based on air outlet temp?
That's a factory set. We really had no control over that. I think that's been determined what the optimum is, and we really hadn't. I know there were dials on there that could be. I think it could be increased a little bit, but when you're bringing in that cold of air, I think 60 seconds is about the maximum that you would want to have.
Okay, great. I don't see any other questions. I'll give it just a second here, and in case there is any other questions, I'll just give a few announcements to mark your calendar for this year's annual conference, September 25th, 26th, and 27th in Schaumburg, Illinois. Check out the website for some exciting things that will be happening this year, and look for some email announcements that will give you more details coming out this week. Oh, and Kevin, we do have a couple more questions, so let me get them out to you really quick.
Okay.
What is the efficiency of these heat recovery units? Oh, hold on, sorry, they're coming in so fast, it's moving my screen a little bit. What is the efficiency of these heat recovery units? I think the question is cutting off. I'm not sure what the second part of this question is, so for some reason it's cutting off. My apologies, so I might have to get that one to you offline.
No, I think I know what they're asking, Sherry. They want to know what the efficiency of the core is. In the winter, I want to say it was somewhere around 60% at that extreme temperature, that extreme cold, and I think it was around 72% in the summertime, because you can use this to also get rid of heat from the outdoor air, but we really don't have that many times when that is happening.
Okay, and then do you have any idea if these cross-flow HXs have greater savings than energy wheels or fixed plate?
I have not compared that. No, it would be a toss-up between the wheels and the energy recovery cores. I would say it would be an equal push. I think it would be more of a space limitation. I think that had we had more room in our on our mechanical prefab that went on the roofs, I think we would have probably gone more along an energy recovery wheel.
Okay, and then it looks like the last question is, a listener would like to know how cold it is there today.
Today, I think we're right around 0 degrees right now, so 32 Fahrenheit. We're in a warm spell.
Okay. Well, thank you very much, Kevin. We really appreciate your time and expertise. And on behalf of the BCA, I'd like to thank everyone for your participation today in today's Tech Talk. Have a great day.